Hello, everybody, and welcome again. Welcome back. I'm glad you're here. This is a discussion about the weight of the robot. How much does it weigh? This is part 2. I do have a YouTube channel. I invite you to subscribe. I think you'll enjoy it. I have a website where I just talk, there's a menu, and I talk about the robot. I always want to mention any physically real object could hurt somebody. If you are managing a physically real object, my advice is to manage it in a manner that is legally allowed and reasonable and safe. And if you can't manage it in that fashion, my suggestion is do not create it as a physically real item. And I asked the mannequins to just help me a little bit, and they decided to put themselves on stilts. Anyway, this is part 2. Now we should take a look here. And again, as we look, let's just see what it shows. This is the Point Reyes National Seashore, I think in California. And this is me trying to explain this robot, this hydraulic cylinder robot, lonely. That's called way out on a limb, and I guess that's where I am, although I hope I'm right. We'll see. This is what I was demonstrating, or going to demonstrate about. I did a robot hand, and I wanted to show that this hand has it has the ability to move like a human hand. It has the range of motion of a human hand, and it has the strength that it can hold up a 200-pound robot. And I wanted to show that the arm of the robot has enough strength to lift up the robot. But when we're talking about a robot operating system, okay, there's a couple of things going on that you need to understand with a robot operating system. One is that there's a computer running the robot, and the computer receives sensory information about the status of the robot. And on the basis of that sensory information, the computer runs programs, and then it creates commands, and it sends the commands out to the structure of the robot to make the robot do what it wants it to do. And one of the reasons why there's been a resistance to hydraulic cylinders is because of the nature of how hydraulic cylinders work. This piston head, the way a hydraulic cylinder works is there's a pressure differential across the piston head. So if there's more pressure here than here, this will go that way. If there's more pressure here than here, this will go that way. The only way that works is that this piston head has to be, the outer circumference of the piston head has to be very closely approximated to the inner circumference of the hydraulic cylinder. And in a lot of hydraulic actions, particularly with construction equipment, this can be 3,000 and 4,000 pounds per square inch, and this whole hydraulic cylinder might be 5 feet long and weigh 3,000 pounds. They're just big. They're huge. And from a sensory viewpoint, it's very hard to do any sensory activity on a normal hydraulic cylinder because there's nowhere in here where you could put your sensory equipment. And the problem is the hydraulic cylinder itself has to be strong and metal. And so anything that you put on the outside of the hydraulic cylinder is going to have a very tough time doing any sensory activity for anything that's inside the hydraulic cylinder. And because of that, my opinion, they just said, you can't get this to work. And I wanted to do something that is different, a point of view that they haven't thought of. And for example, on a 200-pound robot, this maybe needs to be 200 pounds per square inch, maybe 240 pounds per square inch, which in the world of hydraulic cylinders, that's nothing. So this doesn't have to be built where the robot goes out and starts digging up a concrete sidewalk, which is what construction equipment does. The robot doesn't have to do that. And so that allows, if you have lower pressures in here, it lets you do some things that allow you to get a sensory system without the requirement that you have if you're using it for construction equipment. And of course, over here is the hand all straightened out. And this is the issue that I've been working on. You can see here the robot just flexed its legs, it flexed its hips and knees, and that lifts the feet off the ground by an inch or two. And then the robot started abducting its right arm, and that lifts it up. And this is just a drawing showing how that works. I'm showing that when you start abducting the arm, the only way I can do it in SketchUp is to move the arm down. That makes this not right. You can see that this hydraulic cylinder has been extended. And again, I put parts in here that have the opacity reduced so you can see what's going on. And I use different colors. But you can see that this hydraulic cylinder is in the halfway position, and this has broken apart. And if you look at the next one over, okay, you can see that I've taken the hydraulic cylinder and extended it all the way up to here. And the way this mechanical connection works, this traveler arm pivots around this point and swings down. And so right now it looks like you move the arm and then you get the hydraulic cylinder straight. But the truth is, in the robot, what would happen is if the central processing unit told this hydraulic cylinder to extend itself, it would extend itself, and this arm, you see this angle here, this arm would begin to straighten out this angle because this hydraulic cylinder extended itself. And I've got down here 16 inches, so it has moved up in the air about 6 or 8 inches. And so we can go over here to the next one where this hydraulic cylinder has pretty much extended itself about as much as it can. But this hydraulic cylinder now extends itself. And what has happened is the robot, simply by using its arm, it's doing a one-arm chin-up. And it's taken this whole 187-pound robot and lifted it up to it's 16 inches off the ground, which is, go out to the human mimicking robots that are commercially available. None of them can do this. I think because they're like, well, why would you want to do that? But I want a military robot. I want a robot where if it fell over, it can get itself back up again without anybody's help from anybody other than the robot. And the way you do that is with a set of arms that have enough strength to let that happen. And this is what I'm demonstrating. And this is one image of 3. I'll show you the other, mainly because Keyshot is just cool. I like Keyshot. So this is the next set where the robot has gotten itself up about as high in the air as it's going to get. And now we're getting ready for it to let go. See the hand here? And I said to the robot, okay, let go. And the robot said, what are you doing? And it let go. And now we're going to show that with a human mimicking robot, if you build it like you're supposed to, the robot will just say, well, okay. And the central processing unit of the robot will start settling the problem down so the robot doesn't make a complete fool of itself. And the reason that's going on here is if you look at the weight of the robot the robot will swing like this. So the weight of the robot will be adjusted so that it's balanced. So about as much of the weight of the robot is on this side of the hand as is the weight of the robot that's on that side of the hand. So when the robot starts falling, it needs to alter itself so that when it lands, otherwise it's going to land on its left foot and smash its hip into the ground. So we're going to talk through, can the robot do that? That's the next part. And this is a little discussion of at 15 centimeters per second, what happens is this left leg gets abducted out away from the midline, and the right leg gets adducted in towards the midline, and the robot tilts its thorax a little bit to get itself in a position to land, which the robot can do if it's a hydraulic cylinder robot, and the electric motor gearhead robots can't do that. They can't do that with a 187-pound robot. Now, if this is a 187-pound robot, by the way, if this is alloy 2205 alloy stainless steel, this structure right here can support 14,000 pounds. And this foot, the main point of weight support on this foot is this pin right here, where the eversion inversion plate of the foot connects to the lower leg. That pin structure allows the foot to withstand 7,000 pounds of force. This is a robot that the military would say, yeah, I want that robot. Okay, and all of this becomes completely possible if you use these parts this way and you use hydraulic cylinders to run them, because the hydraulic cylinders have enough strength and speed to allow the robot to do what I'm showing here, which is it will swing itself and its hips and its legs and feet over, getting itself. Now you'll see, see where the tip of the fingers are? Right there. And now it's come down a little bit more and it's rotating itself around to get itself ready to land. And this is, we're getting close. Now, a human being, I'm going to have it land the way. The other thing about a human mimicking robot, if you have the proportions of a human being, if you have the joints of a human being, if you have the range of motion of a human being, if you have the axis of motion of the joints to be what human beings have, then when you say, well, what are we supposed to do? It's not hard. You just say, well, if that was you, what would you do? And the reason you can do that is because this robot can really mimic a human being. And the little electric motor gearhead robots can't do that. That's why they have so much trouble with all this kind of stuff and why it's so hard to program. This is easy to program. Just put it where you would put it. Do what you would do. And human beings, compared to robots, human beings are fantastically good, just godlike in their ability to move around and balance and land and walk compared to robots. And so if we should mimic a human being. If we truly mimic a human being, then we don't have to ask ourselves, well, what are we going to do? Because all you have to say is, well, what would you do? And tell the robot, do that, which it can do if you use hydraulic cylinders. All right, and she is holding up a sign. Written on the sign, it says, imitate this note. And she put the sign down as picking up the note, and the note says, stop talking. Oh, I'm out of time. All right, well, we'll stop and we'll start another one.